are mapped up and rendered. Here's a brief outline of what I'll be discussing. I'll go over our system, the background of the system, previous work, the results from our experiment, portion control, and a brief conclusion. Here's our system, which is the absorber water flow station. Our system uses a rotometer and 2 rotometers, manometer, and a Coriolis. Here's an illustration of those. The rotometer and Coriolis measure the water flow of our system, or the flow rate of our system, and the manometer measures the pressure. Here's an SSOC of our graph that was given to us when we switched over to our new system. We are measuring the regions from 9 to 21 on the output and with our associated input. Here's the step-up function of our FOPD modeling. We all have the same step-up for this since it was given by Dr. Henry. And from here we got the values, our gain of 21, our 0.21, our time constant of 2, and our dead time of 2. Here's the step-down function of our FOPD. For our first order sine experiment, we calculated the amplitude ratio and the phase angle in order to find our sine model. And for the delta t, or the delta c, was the angle between the the average for amplitude ratio is 0.3, and the average for phase angle is -36. Here's another example of our sine experiment, which was an average of 0.01 and an average of -270. Here's a Bodie plot of what we use. This is a simplified version of our amplitude ratio versus our frequency, and this is for regions 9 through 13 pounds per minute. And as the frequency increases, the amplitude ratio decreases. Here's for our regions 13 through 17 pounds per minute, and here we have a small spike on around 0.8 frequency, or 0.8 hertz. And it continues to decrease from there. From region 17 through 21, we have a small spike at 0.9 as it continues to decrease as the frequency increases. Here's the phase angle distribution of our Bodie plot. It also continues to decrease as the frequency increases, and it is small. It is consistently 0, 0.1 to about 0.6. And here's the next region from 13 to 17 pounds per minute, and also continues to decrease, but it has a small increase at 0.6 hertz and 0.7 hertz. For the last region, 17 to 21, it continues to decrease, but has small jumps at 0.6 and continues to go down from there. Here's the model for our root locus. We use the gain, time constant, and dead time that we got from our SSOC, 0.21, 2, and 2, and our delta KC was 0.3. These are the results that we got from our model. We all have the same model, so we got all the same values in pound per minute per percent. With the critical damping at 0.3, angle 0, so on. As it goes down, the units are higher to 90. For our first region, 9 through 13, we have just a lot of unneeded data past the imaginary axis on the right. And from 13 to 17, our data stops once it passes the imaginary axis. And it's also similar for 17 through 21 pounds per minute. I'll be going over a few examples of our proportional control. I'll show a few examples at certain angles on the graph, and then I'll show a summarized bar graph of all of our data after them. So the first example is the critical damping model, which we start to use a KC of 0.3, and it settles at 6 seconds and has an offset of 3. Also, all of our models have a delta R of 3, so if we're able to compare them. Here we have critical damping experiment, and for the KC we have on this one is 0.5, with a settling time of 5 seconds and an offset of 2. For the quarter decay model, the KC increased to 9.4, and the settling time increased to 15 seconds with an offset of 3. For the quarter decay experiment, the KC was lower with a higher sinusoidal or with a higher oscillation or more frequent oscillation with a settling time of 15 seconds and a smaller offset of 1. For our ultimate frequency experiment, for ultimate frequency model, it began to oscillate. It started to oscillate at KC equal to 14. The offset is unknown, and the settling time is unknown. For the actual experiment of ultimate frequency, we had a lower KC, and our KC at about 7, starting from 7 up, it has extreme oscillation, which is kind of useless data. For proportional only controller model, we all have the same model, so from regions 9 through 21 pounds per minute, we had a critical damping of about 0.5, quarter decay of 9, ultimate frequency of 14. For the critical damping experiment, regions 9 through 13 pounds per minute, we all had about 0.5, KC value of 0.5. For the quarter decay experiment, we all had about a KC value of 5. And for the ultimate frequency, we had, it didn't go past 1, but we had KC from 9 to 13 pounds per minute of 7.5, 13 to 17, 7.8, and 17 to 21 pounds per minute of 8 KC. In a brief conclusion, we went over the type of system that we worked on, the water flow absorber, the components it used, such as the rhodometer, Coriolis, and the manometer. We reviewed past experiments such as the SSOC, sine, integration, relocus. For our proportional controller experiment, we saw that the KC values decreased for the actual experiment compared to the model, and that the oscillation occurred faster in the experiments than it did in the model.
Hello everybody, my name is Patrick Moss. I'm in the Orchid group along with Oleg Scottson and Nathan Hilton. And we're in the absorber airflow system. And I presented last week about our previous experiments that we've done whenever the system. So today I'm just going to go over the model results and the experimental results for the proportional only controller. Okay, we'll start with the lowest region, and that is from 0 to 10 pounds per minute. And this here is the model results for our proportional only controller. For this particular model, we use a KC value of 6.6% pound per minute. And this was the maximum reasonable KC value for this particular set of parameters, with K equal 0.7, tau 4.5, and dead time of 2.5. And for the minimum reasonable KC value, we used a 0.5 using that same set of parameters. And as you can see, it levels out right here at about 15 seconds, which is our settling time. This system is overdamped, and this is 1/500th decay ratio. It's monotonic. And we couldn't get a middle region, so we skipped to the highest region, which is 20 to 30 pounds per minute. We used a KC value of 8.7, which was the maximum reasonable KC value that we could use, with given parameters of 0.5, 2.7 tau, and 1.6 dead time. This system was overdamped with a decay ratio of about 0.97, so very close to 1. And as far as we can tell, it does not settle as far as our data goes. It is oscillatory. And on to the minimum reasonable KC value, we used a 0.5% per pound per minute. We found this to be overdamped, 1/500th decay ratio. It's monotonic, and settling time is about 5 seconds. And for the experimental results, this is the experimental results for the lowest region, which is 0 to 10 pounds per minute, using KC value of 6.6. And the same parameters as we used for the model. This right here is our output, and it oscillates down, so it is oscillatory. It's pretty similar to the model results, but we would not expect them to be the same due to uncertainties in the system and inconsistencies. We found this decay ratio to be about 0.7, and with no settling time. On to the minimum reasonable KC value of 0.5% per pound per minute. We found this to be overdamped, 1/500th decay ratio, monotonic,